Hello and welcome to today's lecture given by me and Nico, and we would like to speak with you about variational autoencoders and what they have a benefit for personalized medicine and what have Asterix all to do with that.
So that I would like to know as well.
Yeah, so Nico, can you give us an intro into the concepts of variational autoencoders?
Yeah, let me try to give you kind of a high-level intuitive overview of what they are doing, and without going into any technical details. So in general, they are deep, latent, generative models, but I would try to explain it, as in this blog post mentioned down here, I would try to explain that more from the perspective of unsupervised representation learning, which is, I think, what you use it for then at the end. So if you have high-dimensional data, like, for example, images, it's always complicated to find good, like, lower dimensional features that describe what you see on those images, for example. And for us humans, we could typically use language to describe what we see, and that is a good kind of compressed code from which people would actually also be able to recompose an image. And this is kind of the autoencoding perspective on how to learn good latent low-dimensional features of a high-dimensional input. And that's the idea, basically, behind the VAE from this perspective. So you want good features, and good features should actually also be useful to compress the data. And compressing could mean, for example, being lower dimensional than the input. And the goal, of course, is then at the end from this code to be able to reconstruct the original input as closely as possible. And the point with the VAE is that it's a probabilistic framework, so or in this case Alice and Bob, what they have to learn are distributions, actually, encoding distributions and decoding distributions, so at the very end you're able to sample basically new images from that and new latent messages. So the whole system works like that. So you would have an image, then Alice takes that image, then creates a distribution over potential latent codes, then she samples one of those latent codes, gives it to Bob. Bob takes that message, produces a distribution of potential outputs, and then samples one of those outputs, and you train the whole system then jointly so that at the end you're learning to recreate the input with a high probability. So that's the rough idea behind that. And so it works because you have this noisy bottleneck where you sample from, which is typically also much lower dimensional than the input. The interesting bit is, so if you look at don't have to understand that just from seeing this, but this is basically telling you that you have to have a high probability of your input, so you should be able to reconstruct that. That's the general loss function. And there's another part, which is a Kullback-Leibler divergence, which seems a bit weird where it comes from. You can derive it mathematically from the whole objective, but you can get an intuition by thinking about the generative aspect, because at the end, if the whole system is trained, you can just take the decoder network, and then you can use that to generate, basically, to sample new images, or images that you haven't seen, but you could have seen, given the distribution of images that went into the whole system. And in order to be able to sample from that, you need a prior distribution of valid messages that you can easily sample from, and in the case of the VAE, you typically take a spherical Gaussian, that's easy to sample. And now you have to make sure, of course, that the encoder that Alice creates over all the input images she gets creates a distribution over latent codes that matches your prior distribution as closely as possible, and this you can do by enforcing this divergence, this KL divergence between your prior and your posterior to be as close as possible. And if you put that together, then that's the picture that you end up with. And in reality, it's not Alice and Bob. Those are actually deep neural networks that you use for inference and for generation. And that's basically how the loss function looks like. I think you're coming back to this, to these two parts in your part of the presentation. And overall, it's a very interesting model from many perspectives, also from a probabilistic perspective. So if you want to learn more, the original publications are very worth reading. And there's a later introduction to it, and this blog post where I took basically the motivation to explain it this way from. That's also a great resource. And I guess with this, I would hand over to you, literally.
Yeah.
And,
thank you, Nico, for this nice overview about the concept of variational autoencoder. So what's now our perspective as bioinformatician? So we can think of personalized medicine for us as an example where typically we have the aim to define similarity of patients based on molecular and genetic data. So think of a doctor who might have the problem that he would like to know what is the best drug for their gastric cancer patients, and he might have 3 different drugs available, and he would like to define which group of patients should get which drug. And for that, scientists and molecular tumor boards can create tons of data tables like this based on molecular genetic data, and this creates very high dimensional data because we have thousands and thousands of genes in our bodies active, and we have nice tools to generate these kind of data, so-called multi-omics. However, the bioinformatician has then in the end the problem, okay, we have very high dimensions, but we need to define now the similarity on these high dimensions. And for that, we need methods to come from these high dimensions to low dimensional representations where we can then nicely define groups of similar patients, and together with the doctors, we can then say, okay, these groups should get this best treatment options. So this is why we need dimension reduction systems, and this has been around for years and years. And for example, principal component analysis was highly used. Nowadays, one sees typically these kinds of so-called UMAPs, which is also a very common method at the moment. However, they have some drawbacks in comparison to variational autoencoders, or frame it differently, variational autoencoders have very nice properties for these tasks in personalized medicine. And one of these is that in comparison to UMAP, which is a stochastic method, we have we can put in new data, for example, from a new patient, and just put it into the encoder, and we see directly to which group it should belong, to which cancer type, for example. This is not possible with UMAP so easily because it's a stochastic method and does not learn a deterministic function to project this new data. The second very important aspect is that what Nico was showing is that with variational autoencoders we have a generative model. This means that we can go to the Latin space and pick some points, and we have a synthetic patient. Basically, we can sample from the variation auto which we train based on the decoder. And again, this is then, for example, interesting for other bioinformatics analyses, for example, which can use this synthetic data, but also from a privacy perspective. Again, this is not possible with UMAP because for 2 reasons. Again, it's a stochastic model, but also it learns a very sparse low-dimensional representation. That means that the empty spots are basically meaningless in this space. Yeah. So as we now have seen, there are many important advantages of variational autoencoders. Nevertheless, we came up in the transfer project to actually put this into work and building a framework for this. And this framework we named Autoencodex because it's a combination of autoencoder and omics data. And then also we make a play of words with the different types and variants of autoencoders, naming this in Asterix style, like variational autoencoder is then Varix, or we have Stackix and Ontix and so on. But not the names are the most important key features of our tool, but other things. So first of all, you can put in any kind of numerical data and also different numbers of data modalities. And the second, perhaps most important one, is that we are representing with our framework the whole pipeline and not only the training of the variational autoencoder, but also the pre-processing, the visualization of the latent space, and also checking how good are these embeddings performance for a machine learning task. And also importantly, as I said, we also feature different kinds of variants of variational autoencoders, because there have been developments for different tasks, which I will come at the end to this. And finally, we also offer hyperparameter tuning via Optuna, and everything is implemented in PyTorch. After speaking all theoretical stuff, let us have a look also on a example for training an autoencoder. So here I bring you along an example based on the pan cancer data and the genome atlas and so-called TCGA data, where we have 3 different data modalities: gene expression, DNA methylation, and genomic alterations. And in total we have 9,000 features and around about 10,000 different patients with different cancer types, which are colorized here. Probably not so easy to see because there are so many. Nevertheless, we can see then in the training of the variational autoencoder important aspects also, how these variational autoencoders behave during the training when we apply these different terms of the loss function. So in the first phase, we see here during the beta annealing that we have 0 beta, which means that we have no similarity loss. And this will result then, what you see here in the beginning, the expansion of the autoencoder or of the latent space. And then we will, as soon as beta kicks in, have a heavily compressing function on the of the latent space. And this is so heavy that we should also look on the log space for that, where we can see this more easily, that it's first spreading out into the upper right corner, and then as soon as the similarity loss kicks in, it will try to fit this normal distribution as Nico has shown in the beginning. So this is a nice little toy example. I would like to end then also with some aspects with regard to the variants of variational autoencoders and how they can be used in personalized medicine. The first one, which we also implemented in our toolbox, is try to use or try to break the problem of the black box problem of deep learning methods in a way that we incorporate biological knowledge into the decoder part of the variational autoencoders, and only make connections where we have also biological connections between the features, in particular the genes, for example, acting into one molecular pathway. And this makes the latent dimension then for us explainable, so we can see then actually what is going on there. So this is one thing. And the other I would like to point out is that we also implemented the idea of so-called cross-modal autoencoders. And here the idea is to learn a joint latent space for 2 different data modalities, so that one is in the end capable to translate between 2 data modalities, for example, between mutation and gene expression, so that we can see how mutation might influence the gene expression. So these are very cool things which we are playing around at the moment to come then also with a publication for our toolbox. And for that, mainly Max is also heavily involved, who is a contributor in Autoencodex. But nevertheless, we have also quite a few others who are helping us with the development of the framework. And we would like to thank them. And
thanks a lot. Thank you.